In this tutorial, we will explore how 3D surface metrology can be used to inspect surface defects and characterize surface texture. We will look at three relevant ISO standards. ISO 8785 for surface imperfections, ISO 21920 for profile surface texture, and ISO 25178 for areal surface texture. We will also see how 3D measurements can complement conventional 2D imaging and tactile measurement methods. Let's start with surface imperfections. ISO 8785 describes a wide range of imperfections, including scratches, grooves, cracks, pores, dents, deposits, and craters. These imperfections can differ not only in their lateral dimensions, but also in their height or depth. This three-dimensional nature is important when we want to detect and quantitatively characterize them. Surface inspection is commonly performed using conventional 2D cameras. This has clear advantages. The hardware is inexpensive, well-established, and a large range of image processing tools is available. However, the appearance of a surface defect in a 2D image strongly depends on illumination, surface reflectivity, and viewing geometry. The three images shown here, for example, all represent the same defect under different imaging conditions. Its appearance changes significantly, and although we can measure lateral dimensions in the image, properties such as defect height or depth cannot be determined directly from intensity information alone. This is where 3D surface metrology provides additional information. Instead of evaluating only image intensity, we measure the actual surface topography. Individual imperfections can therefore be characterized quantitatively by parameters such as length, width, height, depth, or area. And over a larger surface, we can determine quantities such as the number or density of imperfections. The key advantage is that the classification can now be based on physical geometry rather than only on the optical appearance of a defect. Let's look at a few examples. The first is a blister, a local raising of the surface. In the 2D images, the appearance changes considerably with the imaging conditions. The 3D measurement, on the other hand, directly reveals the topography and allows us to quantify the lateral dimensions and height of the blister. The next example is a scratch. Its length and width may be visible in a conventional image, but its depth is much more difficult to determine. The 3D measurement reveals even very shallow surface recessions and allows the scratch depth to be measured directly. This can be important when scratches with a similar optical appearance have very different functional relevance. Surface imperfections can also combine raised and recessed regions. This example shows a score. The 2D image clearly indicates a defect, but it does not provide an unambiguous description of its geometry. The 3D topography immediately shows both the raised material and the depression, and allows their dimensions to be quantified. And finally, not all imperfections are isolated features. Corrosion, for example, may affect an extended area. Here, 3D measurement can characterize both the spatial extent of the affected region and the associated changes in surface height. This illustrates why surface imperfections are fundamentally a three-dimensional measurement problem. Individual defects are only one aspect of surface quality. We now move from discrete surface imperfections to surface texture measured along a profile. For this, ISO 21920 provides the current framework for profile-based surface texture characterization. Profile roughness has traditionally been measured using tactile stylus instruments. A small stylus traverses the surface and records a height profile. From this profile, parameters such as RA, RZ, and RQ can be calculated. Tactile profilometry is well established in industry, relatively affordable, and deeply embedded in technical drawings and manufacturing specifications. For this reason, tactile measurements remain an important reference for profile roughness. However, contact measurement has limitations. It can be relatively slow. It physically touches the surface, and only individual profiles are acquired. For production applications, optical measurement offers an attractive alternative. It can operate without physical contact and can acquire surface data much faster. But this leads to an important question. Will an optical measurement produce results that are comparable to the established tactile reference? The answer cannot simply be assumed. It has to be validated for the surface, measurement conditions, and parameters of interest. To investigate this, we performed comparison measurements on three different surface finishes: a milled surface, a ground surface, and a lapped surface. Each surface was measured both with a tactile reference instrument and with a Heliotis non-contact 3D measurement system. The same profile roughness evaluation was then applied to the optical data. Let's look at the results. The first sample is a milled surface with a raw value of approximately 1.4 micrometers. The tactile reference gives an average raw of 1.409 micrometers, while the optical measurement gives 1.482 micrometers. This corresponds to a difference of approximately 5%. The distributions also show the repeatability obtained from 10 parallel measurements. For the ground surface, with a raw of approximately 1.6 micrometers, the agreement is even closer. The tactile measurement gives 1.620 micrometers and the optical measurement 1.653 micrometers, a difference of about 2%. Again, the distributions show the results from repeated measurements. The third example is a much smoother lapped surface. Here, the roughness is only around 60 to 70 nanometers. The tactile reference gives 66 nanometers, while the optical measurement gives 62 nanometers. Even at this much smaller roughness level, the two methods show good agreement for this particular surface. These examples demonstrate that optical and tactile profile measurements can correlate closely. However, equivalence should always be validated for the specific surface and measurement task. Different measurement principles interact differently with surface slope, reflectivity, spatial wavelength, and filtering. So far, we have reduced the surface to individual profiles. But a surface is two-dimensional in the lateral direction. This brings us to the third topic, areal surface texture according to ISO 25178. A single profile represents only one line across a surface. For many surfaces, this is not sufficient. Depending on where the profile is taken, important peaks, valleys, or other features may be included or missed entirely. Areal measurement instead evaluates the complete three-dimensional surface. ISO 25178-2 defines parameters for describing this areal surface texture, including height, spatial, hybrid, and functional parameters. This provides a much richer description of surfaces whose function depends on their three-dimensional structure. This becomes particularly useful for engineered surfaces. Surface texture can influence functions such as wetting and self-cleaning, friction and lubrication, fluid flow, optical appearance, or haptic behavior. The examples shown here contain deliberately manufactured microstructures. Instead of describing such a surface by one or several individual profiles, an areal measurement captures the complete geometry of the functional structure. The appropriate ISO 25178 parameters can then be used to quantify and monitor that surface. The examples in this tutorial illustrate a broader advantage of 3D surface metrology. The same measurement data can contain information at very different scales. We can identify and quantify surface imperfections. We can extract profiles and evaluate profile roughness according to ISO 21920. We can characterize complete areas according to ISO 25178. And at the same time, we can measure dimensional properties such as height, volume, planarity, position, or warpage. In other words, a single 3D acquisition can provide information about roughness, defects, and geometry. For more tutorials, visit heliotis.com.